So let's consider a problem that we've thought about before, which is when I throw a ball straight up, what happens, right? So there's the ground. Let's put it on level ground, huh? So there's the ground, just for reference. Let's say the ball starts at some location with some like initial speed upward. Right, there's the initial, and then sometime later it moves upward and has some v final. Let's move that whole thing down just a little bit. No, no. All right, there's my v final. Let's make v initial a little longer. There. Fabulous. Okay, so why did it slow down? Well, because it's in free fall, and I know everything in free fall accelerates downward at g. Right? So you could solve this problem if you knew a v initial and looking for a v final. You could solve the problem using kinematics. But you can also solve this using the work energy theorem, right? Where we could say the work done on this thing is equal to the change in its kinetic energy. And the work done on this is the work done by the force of gravity, right? So the acceleration downward is really because during this whole motion, I could draw a free body diagram quickly. During the whole motion, there's weight acting downward, right? So I could calculate what is that work and how does that change the kinetic energy, right? So this is another way to solve the same problem using the work kinetic energy theorem. So I want to fill that out quickly. So we could say, let's see, the work done, remember that work is force parallel times a displacement. In this case, it's in the y direction, so I'm going to say delta y. And in fact, that displacement, let's make it green, is up, right? That's my delta y. So the force is actually anti-parallel to this. We could even write this in one more. We could say that's F, we'll do that. F delta y times cosine of the angle between them. And the angle between them here is 180 degrees. Right? That's 180 degrees. That's where we're going to get a negative sign. So I could do another line and say the force is mg delta y cosine of 180, which is negative 1. So let's plug this. This is the left-hand side of this equation, right? So the work kinetic energy theorem says this. Work equals delta K. The work in this case is minus 1. I don't need the 1. I'll just say minus mg delta y, which I could write as y final minus y initial equals delta K. And I want to suggest this. So if I put the negative sign, we'll just leave it this way for now. So I could move that whole thing to the other side of the equation, right? I could say, what if I add this term over here? That gives me 0 equals delta K plus mg y final minus mg y initial. Now, you remember how we defined kinetic energy? We're worked out for constant acceleration motion what the right-hand side, what work is done, really, right? And we noticed that it was a change in some quantity that we defined as half mv squared. Now look, action under gravity, which is constant acceleration motion, gives me a change in some other quantity, which we could call, sometimes we call it capital U. In this case, it's mgy, right? So I could rewrite this equation as work equals delta K plus delta U, right? Specifically, this is a specific kind of U. We call it U sub G. All right, so instead of including the work done by gravity, I'm now adding that to the other side of the equation. This is something that we define. Let's use a different color. This is a potential energy. Specifically, this is gravitational potential energy. Has the same units as kinetic energy, has the same units as work, because it is exactly the work done by gravity. Well, it's the negative sign of work done by gravity. All right, so instead of including the work done by gravity, we're including another term in energy. So including gravitational energy lets us account for the gravitational force. So this is useful. We'll see this in a second. We'll see in a second. So I could now define something that we call total energy. You can say capital E. It would be kinetic energy plus potential energies. All right, specifically, in this case, gravitational potential, but there are other kinds of potential that we'll talk about. And I could rewrite the work energy theorem as work done equals delta E. And again, I can either include the work done by gravity in the work, or I can not include it in the work, and I can include it in this energy. So let's talk about, when can you define a potential? And the answer is anytime the force acting is conservative. Okay, what do I mean by a conservative force? All I mean is that that the force really, it's that the potential energy does not depend on the path taken to get there, or the work done by that force does not depend on the path that it takes to get from one place to the other. Let me typify this by giving an example of a force that is not conservative. All right, so the work that it takes to push a box around a room depends on what path you take, right? If you take a straight line path from one point to another point, let me draw that. All right, if I take a box and I'm putting it over here, right? This is initial, this is final. If I take the straight line path, or if I take some zigzaggy path, if there is friction involved, the zigzaggy path will cost me more energy, right? Because I had to push it further. So work done by friction, we'll say this. Work done by friction is path dependent. All right, but if I'm lifting a box, let's say I'm taking it from the first floor to the second floor, the work that I do against gravity only depends on the work I do against gravity. Remember, when you carry a box across a room at a fixed height, you're not doing any work on the box, right? It might cost you energy to walk across the room, but that's because you're fighting against friction the whole time, right? So that work is actually friction, and that's lost as thermal energy. It isn't going to the box. So it doesn't matter if I'm going from the first floor to the second floor. The gravitational change doesn't matter whether I go across the hall and then go up the stairs, or I go up the stairs at one end of the hall, right? So friction here is non-conservative. And gravity is conservative. Really, the difference again is if the work done by that force is path independent or path dependent, right? Path dependent is non-conservative, and path independent is conservative. So this work energy theorem up here, All of the potentials that I include, let me back up and say, I can define a potential for any conservative force. We'll see springs in a little bit. Springs also are conservative force, so I can define a potential for that. Electromagnetic forces are conservative, so I can define a potential with the forces due to electric fields and the forces due to magnetic fields. So I could include that in potentials. But anything I can't include in a potential, I have to include in work. So I could say work done by non-conservative forces. Conservative. So the work done by non-conservative forces is equal to the change in the total energy of that system, which includes potentials. So let's look quickly at another example. So example 4 here says a ball is thrown directly upward with some initial speed. How high does it go before falling back to Earth? Okay, so we could do this two ways. We could either talk about kinematics, which is what I just suggested. So we're throwing a ball upward with an initial speed of 3.7 meters per second. And we're asking how high does it go? So V final here is 0. And the question is, what is delta Y? So we can solve this at least 3 ways. One is to consider the work done by gravity. Another is to consider kinematics. Right, we know the acceleration, and another is to do what this is saying is conservation of energy. All right, they're going to look very similar. You know what? Instead of doing those first 2 ways, again, all 3 of these are solved on the handout. I think I'm just going to solve it 2 of those ways. So one of the ways is let's do kinematics. Okay, so we could say y final equals y initial plus vy initial delta t. Ooh, that's not going to help me. And you'll see why. Half g delta t squared. All right, why doesn't that help me? Because I don't know how long it's in the air, right? So I could do that, but I would have to solve the time first. So let's consider another equation. All right, again, I could do that and solve for a delta t and then plug into the v final equals v initial minus gt equation. But there's another equation that's going to be super useful, and that's this. Vy final squared equals vy initial squared minus 2g delta y. I could use this to solve for delta y. Let's do that quickly. V final is 0. V initial is 3.7 meters per second squared minus 2 times 9.8 times delta y. I can solve that and get a delta y of, if I round it, I think I get 0.7 meters. Oops. 0.70 meters. Okay, so here's another way I'd like to solve it. Let's use our new work energy theorem. Right, so not the work kinetic energy theorem, but the work energy theorem. Okay, so on the left-hand side, I have the work done by non-conservative forces. Are there any non-conservative forces here? Well, if there were drag is a non-conservative force, and I would have to include that there. There is no drag, though. It doesn't say that, but generally we ignore drag. At these speeds, 3.7 meters per second, you can pretty much ignore it. Unless you're throwing like a ping pong ball or something that's really light but really big, right? Like a hollow, like child's softball. But let's assume here We'll write it in blue. Assume no drag. That means that there are no non-conservative forces. So that 0 equals delta E, which is delta K plus delta U. Okay. Okay, so let's fill that out. 0 equals K final minus K initial plus U final minus U initial. And again, there's only one potential energy here, and that is gravitational potential. In the future, we might have to include more types of potential. Okay, so we can fill this out. Let's giving myself a little more room every time. Half mv final squared minus half mv initial squared plus mgy final minus mgy initial. Right? Remember, u sub g is mgy. Sometimes we call this mgh for height. Just know that height and y are the same thing. Okay, this is great, and I'll tell you why. Two of these things are 0, right? We're starting at the ground, so let's call this point y equals 0. That means y initial is 0, so I can call that. That's gone. Y final, I'm going to the highest point here. Y final is 0 as well, so I can make that go away. Sorry, not y final. V final is 0. Y final is non-zero. That's actually what we're solving for. Okay, so that gives me two things. That's this term and this term add together to be 0. One of them's negative. That's fabulous. That way I'm not going to run into a problem here. So I could add this term over here. So I've got half mv initial squared equals mg y final. Look, the g's go away, right? I can divide by g. Sorry, not g. G matters for sure. The masses go away. That's good, because objects in free fall, the mass doesn't matter, right? The mass doesn't matter for objects in free fall, so the mass couldn't matter here either, and it doesn't. Okay, so if I solve this, let's just plug in and solve. Half v initial is 3.7 meters per second squared, meters per second quantity squared, or parentheses squared, times 9.8 meters per second squared, times y final. And if you solve that, y final is 0.70 meters, which is the same answer. Good, right? Was one of these approaches more right than the other? Absolutely not. If you actually solve our original expression, plug in vy equals 0 and solve the original expression for y final, you get the same algebraic expression. This is just two approaches to the same problem. So at this point, you could choose whichever one is you're more comfortable with. In the future, there will be problems where kinematics is actually very cumbersome, but energy is super useful. So we'll see that in the future. Also, we will be able to rearrange this equation into something very meaningful. Actually, we'll define another law, another physical law based on that. So look forward to that.